Chapter 7, Part 2 for air mass and synoptic climatology. Here we'll just look at atmospheric blocking and how that helped set up the Boulder floods of 2013. We'll also look at alignments of the jet stream, what's called zonal alignment versus meridional, how that works with what's called the Arctic Oscillation, and also how sea surface temperature can change the position or the alignment of the jet stream too. Atmospheric blocking is an atmospheric setup that encourages a certain pattern to persist for days or weeks. Migratory weather systems are forced to go around the blockage. So usually it's a high pressure cell that blocks or tends to block or force the jet stream into a certain alignment, since these high pressure cells are really large and slow moving. However, it can be a cutoff low too, or other times it can be a combination of a cutoff low and a high pressure cell. Here's one called an omega block that simply looks like the Greek letter omega. And you see a high pressure cell here in the middle. And this would be looking at anomalies at 500 millibars, so looking aloft in the atmosphere what the pressure systems are, because that's really going to dominate which way the jet stream is going to flow. So in this case, if you have a high pressure here, low pressure is pinned on either side, the jet stream is forced to come and do a high amplitude wave up and around that high pressure zone. If you live within this high pressure zone, you will not be seeing any weather for quite some time, because all the storms associated with the jet stream will simply traverse around you. So dry conditions underneath that high, and if you're underneath these low positions, you're going to have generally stormy weather as a result of being in an area of low pressure and uplift in the atmosphere. Between these two regions, A and B, which one will see higher than average surface temperatures while this omega block remains in place? Well, if you just look at the overall prevailing wind direction, and so if we look on the right side of the high, the winds are generally going to be pushing from north to south. You could probably expect, while this omega block is in place, to have a strong northerly winds, colder than average conditions at point B. And on point A, just the reverse, you're going to have a southerly wind for the time this omega block's in place, probably warmer than average conditions as a result of that wind direction. Here's just looking at an omega block in real data. We can see one right here, high pressure at 500 millibar surface heights here, and then low pressure pinned on either side. So this would be that blocking high that forced air to go up and over that ridge, which led to persistent conditions here. Here's another example at 250 millibars, so way up at the level of the jet stream. What they're showing here is that warm air was wedged underneath here, which forced the jet stream, which always follows the temperature gradient, forced the jet stream far to the north, giving you this omega block in place, which tends to sit there, and so it leads to more persistent weather patterns, which could last days or even weeks. Here's a different form of block called the Rex block, after the person who came up with the idea. Best seen at, again, 500 millibars, the midpoint of mass in the atmosphere. This block features a high north of the low. Generally, dry conditions will prevail under the high. As we know, high pressure is generally associated with sinking air, and then generally wet conditions under the low. Low pressure is generally associated with rising air. So if you look at the wind patterns around this high and low, air is going to flow clockwise in the northern hemisphere around the high. It's going to flow counterclockwise around the low. So the winds in here are actually east to west, and it turns out you're going to have a lot of moisture where the position of these are. Florida's right here, just to the southwest of the low. You're going to be pulling up a lot of moisture off of that really warm, moist air mass over the Caribbean and pushing it into the central east coast of the United States here. So as long as this Rex block persists, and it lasted quite a while, you're just going to be having floods in these areas that are generally associated with the low pressure, and also giving you the moisture advection off the ocean to your land surface too. Now, the Boulder floods of September 2013, the atmospheric setup was similar to a Rex block. So we do have a high pressure up here, a high pressure ridge just north of the border between US and Canada, kind of near Washington State. And you do have a cutoff low existing here, just a little bit west of Colorado. And this is an average chart taking over the period of time that the floods happened in, which is roughly a 6-day time frame. So if you look at how flow moves around a cutoff low, as we've talked about, it's going to have an eastward motion here. So it's going to be helping drive Gulf of Mexico moisture right up into Colorado and really forcing it to get pinned against the mountains that are to the west of that flow. Here's looking at a better position on specifically September 12th. And again, I'm going to put in my animation. Here's your cutoff low. Here's flow around a cutoff low, cyclonic. Here's flow around your high up here that existed, again, at the US-Canada border. And so again, this really helped promote, first of all, scooping up really moist tropical moisture. And I will mention here that the moisture amounts that were found in Colorado were more signature of the deep tropics. There were 4 standard deviations from normal. Extreme amounts of moisture was definitely a big part of the boulder floods. But also dynamically, this kind of Rex block situation where it's scooping up moisture and then forcing it upslope up our mountains. And since this Rex block didn't move in time, it stagnated there. So you consistently had an upslope for 6 days, which is very unusual for us. This graph is just looking at the rainfall amounts around Boulder and the associated foothills. Generally speaking, we have 16 to 20 inches here, with the whitish colors, the light purples being the heaviest amounts. Towns are shown as red dots here. These white stars are actually just showing where we have equipment that can measure both the rainfall rate and the amount. So usually you typically have a rain gauge, which measures how much rain might have fallen over a given period of time before somebody emptied out the bucket. However, other instruments like a disdrometer can actually measure how fast rain's coming in and the size of the raindrops, giving us a little more information about the type of storm and the microphysics and the clouds happening there. And here's just an example of some of the damage from this. Here's this person's septic tank that got dug out by the water. And of course, their house had some issues here with the digging and the erosion from this event. Here's a road getting eroded away. This event was a 1,000-year rainfall anomaly, so a very uncharacteristic amount of rain, but only a 100-year flood anomaly. And it did happen in the fall, and initial conditions were really dry before this flood happened, so you could assume that the ground could have taken in a certain amount of moisture before it became saturated with this flood. Also, it probably would have been much worse if it happened with an existing snowpack in, say, the spring. Here's looking in Greeley at the South Platte River, which isn't shown in the first image, but after the river literally changed course because of the amount of flooding, you did have a substantial amount of water that actually dug out this road. So this tends to make you think about how extreme events actually shape the landscape, maybe more so than long-scale erosion. In this case, a lot of our riverbeds dug out to enormous depths from this one event that really was going to dominate those river drainage landscapes for hundreds and hundreds of years as a result of this single event. All right, another type of block that's kind of interesting is what's called a cutoff high. These are relatively rare, and if they do happen, they tend to happen over the southeast in the summer. So high pressure is associated with, again, descending air, nice warm conditions, dry conditions. What happens here, since air has to go clockwise in the northern hemisphere around high pressure, and the nice weather's inside the high pressure, outside you can often you have enough moisture, you're digging up moisture from the Gulf of Mexico, pushing it around this high, you can actually get thunderstorms to form around the high pressure that circulate clockwise around there, and that's why it's called the ring of fire. Split flow is something that happens a lot, especially in Colorado. The jet simply splits around a large high, so the storm tracks will either go to the north or to the south of the split, and if you found yourself underneath the high, you will not see some weather until the split flow moves on. So these two graphs, the first one up here in the upper right is showing your kind of typical zonal flow for the jet stream, and that means more of a west to east component to the jet stream. It doesn't have a lot of curvature going up and down, which would be considered meridional movement, but instead it's going pretty much west-east with a little bit of wiggles. And this usually makes the weather systems along the jet stream move kind of quickly along here. So your weather pattern will be rain for 5 days, then clear skies for 4 or 5 days, etc. A pattern that will develop, which is typical. If, however, you get an atypical high amplitude pattern, otherwise known as a meridional pattern, where the waves have high amplitude, you're going up here with the jet stream and then well down to the south and then well back to the north. This will result in warm conditions for Alaska because you're pushing warm Pacific moisture up towards Alaska, and then it's going to result in really cold conditions for the eastern U.S. because you're continuously pushing Arctic air towards the eastern U.S. over time. At the same time for the eastern U.S., this particular pattern, here's your trough, your next ridge is over here. This would be an area where you're developing cyclone after cyclone, and if you develop a cyclone here, you're going to get what's called a northeaster, which means that the cyclone will wrap cyclonically, giving you flow off the really cold, moist Atlantic into the northeast part of the country, giving you not only cold from the Arctic, but also moisture. The combination makes a lot of snow. So this happened in 1977, 1978, that winter, and also it happened again in 2014 into 2015. That winter was well known for being a brutally cold and snowy winter for the East Coast. So the snowfall totals were pretty anomalous all throughout the East Coast, from New York, say, up through Boston and beyond. This is called the Arctic Oscillation. This flip-flop of the jet stream being more zonal, with nice, quick-moving, vigorous storm systems coming through, to being more meridional, where it's kind of locked in position with these big, high-amplitude waves. These waves can really lead to persistent weather. You know, this area over here is going to have a southerly wind persistently warm for that period of time it's locked in, and it could be half a season or more. And this area over here is going to be consistently cold as they have a north wind. This Arctic oscillation is another one of these natural variability modes that happens in the planet. It's worth noting that many of the models are suggesting more meandering and therefore more persistent weather patterns in the future. Now, a few years ago, we had what was called the warm blob off the coast of the Pacific, and this was a highly anomalous, large area of warm water that was several degrees warmer than typical. So how does that affect things? Warm anomalies at the surface tend to produce high pressure aloft, expanding the air column up. As a result, this feeds into this meandering nature of the jet stream. If you have this warmth here causing high pressure aloft, that means the jet stream has to turn clockwise in the northern hemisphere around that. So typically, if you push the jet stream way up in one area, the next thing you'll know, it's going to dive way farther south just next to you, creating a nice high amplitude wave. So how much this warm blob fed into the extreme nature of the East Coast winter that we looked at is really a matter of debate. How much of this meandering maybe is due to global climate change versus how much is due to this warm blob of oceanic air versus how much is due to a natural oscillation known as the Arctic Oscillation. These are hard things to tease out. I'll end with this, just looking at the sea surface anomalies in late March 2017, just to show that that warm blob is not there anymore. In fact, it's kind of a cold anomaly off the coast there now. So again, these natural variability modes are kind of interesting. The other thing you can see now is that we are starting to head towards an El Nino. At least that's what it looks like right now, with anomalous warm water in the eastern Pacific developing. Key points from this lecture: atmospheric blocking can shift the jet stream, leading to persistent weather patterns and floods and droughts. Of course, we all know we want to look at the global climate change and how the globe as a whole is changing, but regionally it's quite important to understand how the atmospheric circulation might change in the future. Sea surface temperature patterns upstream of a region can certainly affect the jet stream pattern because the oceans have such high thermal inertia. If you have anomalous warmth like that warm blob, it can change the path of the jet stream for quite some time. So you also have to understand what's happening in the oceans as far as sea surface temperatures.